Okay, so what we are talking here on those classes is that is known as the Coulomb's law. Coulomb's law is the law that we use to identify, to figure out, to determine what is the magnitude of the electrostatic force that two charges are experiencing. And the finding that Coulomb had is that this magnitude is direct proportion to the product of the two charges and direct proportion of the inverse squared of the distance between the two charges. So those Q1 and Q2 are the magnitudes of the charges, and R is the distance between the two charges. When you put those all direct proportions together, you have the formula that is K, where K is the Coulomb's constant, Q1, Q2 over R squared. Now, force is a vector quantity. So we identify the direction, and any vector has magnitude and direction. We identify the direction using the magnitude, using the general law of electricity, which is saying that same charges will repel and opposite charges will attract each other. Note here that we have stated in the very first explanation of this topic, or forces and fields, that we said that any charge, positively or negatively charged, will always attract a neutral charge, because what is happening in the neutral charge is the induction, which is the rearrangement of the charges within the object. And then the rearrangement is always happening opposite of what you have, so opposite charges will attract each other. This is why a neutral charge is always attracted by a charged object, no matter what is the nature of the charged object. Okay, so the line in which the electrostatic force is experienced is that imaginary line between the centers of the two spheres, because usually we're talking point or spheres charges here, the center of the two spheres. And if it is attraction, is toward each other. If it is a repulsion, is away from each other. So if you have charge 1 here and charge 2, then that imaginary line is a line that goes through the center of the two charges. And if those two are, let's say, opposite charges, so positive and negative, then the force is attraction, so it will be a force that goes like this. And if it is two same charges, let's say two negative, then the force will be something like this. This is what I mean by toward each other and away from each other when they are attracting. Attract and repelled. Okay. So when we have two charges, it's kind of easy, because what we do is we say that, okay, what is the magnitude of charge 1? What is the magnitude of charge 2? And then we can find what is the distance and the distance between, and then we can find the magnitude of the electrostatic force that those two charges are experiencing. The problems becomes more complicated, quote unquote, when we have more than two charges. So when we have three charges, 1, 2, and 3, that are, let's suppose, in a straight line, what we do is we apply that is known as the superposition principle. The superposition principle in every science course that you will take will be taking the charges, in this case, one by one. So if we are looking for the electrostatic force net at charge 1, then what we are doing, we are placing ourselves into charge 1 and then asking ourselves, what is the force that charge 1, the charge of our interest, is experiencing as a result of the presence of charge 2, supposing that charge 3 doesn't exist. And since those two are opposite charges, then the force is an attraction force. So you will have a force that charge 2 is exerting on charge 1, supposing that charge 3 doesn't exist. And then you will say, what about the force that charge 1 is experiencing as a result of charge 3, supposing, this is superposition, that charge 2 doesn't exist. So since between charge 1 and charge 3, they are opposite charges, then again will be attraction. So will be a force that is, again, attraction. And this is the free body diagram of the electrostatic force that charge 1 is experiencing. On this case, what do we have is a 1D situation. And what do we do when we have a 1D situation? 1D means that in one direction, in the same line, collinear to each other, maybe parallel to each other, but in the opposite direction or in the same direction. We assign a positive direction, and you can assign any positive direction, anything that fits your situation, and then you add, always add, using positive or with positive or negative number. The positive will be the one that are on the same direction as the positive direction that you are assigning, and the negative one will be the forces that are in the opposite direction with it. The magnitude of those forces is found using Coulomb's law, KQ1, Q2 over R squared. Keep in mind that on this case, when you are calculating the radius or the distance between 1 and 3, you will add those two distances together. Another question that is very typical into when we are dealing with Coulomb's law is when we have those charges, and on top of everything that we said today, we will apply the general or the conservation law of charges. So a situation in which you have to apply the conservation law of charges, which, by the way, is one of the principles in your principle list at your data booklet. One of the, when we apply it, you will see something like this, that charge 1 is in contact with charge 2, charge 2 is in contact with charge 3, charge 1 is in contact with charge 3. So what you will do on those cases, whatever steps they are saying, they are telling you, you will go that the new charges, so let's suppose that we are in contact charge 1 and charge 2, the new charges will be equal to each other and will be with the average, arithmetic average of the two charges. So on this case, you will consider what is the nature of the charge. So if charge 1 is positive, then you will say positive 3.2. If the charge 2 is negative, then you will say plus, open brackets, negative, whatever, of charges. So if the original charge is, let's suppose, positive 8.0 coulombs and charge 2 is negative 12.0 coulombs, then they are in contact with each other, then the new charge will be new, this is prime, Q1 equal to Q2, and will be Q1 plus Q2 over 2. Know that what we are doing here is we are applying the conservation law of charges. So this will be plus 8 plus negative 12 coulombs over 2. So the magnitude and the nature of the new charges will be minus 2.0 coulombs. And after you go through this process for whatever steps the question is asking you, if you want more, you can refer to the previous examples. Then you will apply the superposition principle to draw the free body diagram, and then from there find the magnitude of the electrostatic force. And if it is a 1D situation, which usually is in 99% of the cases is, and then you will assign a positive direction and add using positive and negative numbers. This is in terms of 1D. So what do you see in a 1D situation is pretty much those type of problems. Okay, so when you have two charges, different nature, find the electrostatic force. When you have three charges, apply the superposition in a straight line. And then the fourth type is when you have to apply the conservation law of charges. In terms of 1D, those are the typical questions that you will see. Another application, or the way that we see Coulomb's law applied, is when the charges are not in a straight line. And what this will end up being is a 2D situation. So if we have on the first examples, we had a 1D situation, now we will see a 2D situation. In a 2D situation, we'll follow exactly the same things, the same logic. So we will see what is the free body diagram at the charge of our interest, draw the free body diagram, figure out some angles, and then, since it is a 2D situation, the best way to do is complete the table of components. Why do I like that table of components? It's structures. It doesn't allow you to make mistakes. And if you practice it often, then you will take you no time to complete that table of components. And then after you find the horizontal and vertical, you can find the magnitude and you can find the direction. The two subtypes into 2D situations, so if the first one or first examples were 1D, in a 2D situation, the two subtypes will be when the charges are at the vertices of a right angle triangle. So if they are at a right angle triangle, then you will have a situation like this. When I say vertices, vertices are those points here. So let's suppose that we have a QA at point A, QB at point B, and QC at point C. And let's say that QA is negative, QB is positive, and QC is positive, and QB is negative. So we are looking for force net at QA. Then you will step in at the charge of your interest, at the object of your interest, and then you will take the charges one by one in the relation to your charge of interest. So you will say between A and B, what is the nature of the electrostatic force? Is attraction or is a repulsion? It is a repulsion force. It is a repulsion force because the two charges have the same nature. And it is along the line. And since AB is, the line AB is going up north, then this is why is it going up north. And then you say, what is happening between QA and QC, what is the nature of the electrostatic force? Is attraction or is a repulsion? And since the nature of the charges is opposite, will be attraction and will be along those lines. So this force, Fc, which for simplicity, I'm just saying Fc to indicate that is the force that is experienced as a result of charge C, is AC and this line that represent force Fc are parallel to each other. So this is parallel to this one. So after that, we find the magnitude of the force, and then we find the angle, this angle here, angle alpha, which will be the same as the angle that the FC is forming with the vertical axis or south axis in this case. And then we complete the table of component: horizontal, vertical, FB, FC, and Fnet. After we find the horizontal and the vertical component, we compose the vector, which is just taking the magnitude and figuring out the angle that it is forming with the one of the axes. And then we define what is the force net at point A. The second subtype that we have on the 2D situation is when we have the charges in an equilateral triangle. We saw that example the other class. So just keep in mind that equilateral triangle is a triangle that sides and angles are equal to each other. So that means that the length of, let's say, ABC, AB, AC, and BC are equal to each other. And the angles, angle A is equal to angle B, is equal to angle C, equal to 60 degrees. And then you have charges, QA, QB, QC. And this is a bit easier because the forces will create a 60 degree angles either with horizontal or vertical. You have to make that judgment based on the nature of the charges and the interaction between them. After you draw the free body diagram at the charge of your interest, then you can again, since it is a 2D situation, you can figure out what is the horizontal component of force net and vertical component of force net using the table of component, and then from there find the direction. Now, so up to now, this is part of applications of Coulomb's law, but now from now on, we will see that a different type of applications of Coulomb's law, in which we have charged object, usually is a sphere, a light sphere, that is in equilibrium, is tied with a string, a non-conducting string, and it is forming a certain angle with the vertical line. So those are known as the applications of Coulomb's law, a charge in a non-conducting string. If you want to see like a different example solved, you have that explanation on D12, you can refer to that. But on those type of questions, what you will notice is that the mass of the sphere is given, and usually is a very small mass, is given usually in grams. So let's suppose that the mass of the sphere is, let's say, 2.30 grams. and it is forming as a result of an electrostatic force that is applied into this sphere. I have a charge Q that, let's say, that is whatever, is forming with the vertical axis an angle theta of, let's say, 12 degrees. Usually the angle is a small angle, okay? What we are finding here is what is the magnitude of the electrostatic force, okay? Now, since the object of our interest, which is the sphere, is in equilibrium as a result of the presence of that electrostatic force, when you see the words equilibrium, suspended, or it is rest is another one, or is in a static equilibrium. Sometimes we use static equilibrium. Then, as soon as you see this word, this is one of the key words. Those are one of the key words to identify and to give you the clue that force net, that this object that is either in equilibrium, is suspended, or is it at rest, is equal to 0. And as soon as you see that you are discussing, you are talking, you are analyzing the force net, then the natural logic brings you into, okay, that means that I have to draw the free body diagram of this object. So as soon as you see the word equilibrium, suspended, at rest, then you have to think force net is equal to 0. And since you're finding force net, and force net is the vectorial sum of all the forces that the object is experiencing, then a natural step will be, okay, I will see what are the forces that this object is experiencing. And how do we see that? By drawing the free body diagram. So we'll draw the free body diagram of this object. And now, since the mass of the object is given, that means that you have to consider it. And when you have an object with a mass, what is that universal force that the object is experiencing? What is it? It's gravity, the force of gravity. So you have a force of gravity that always goes from the object toward the center of the Earth. And the magnitude of it is mass times acceleration due to gravity. Great. What else do we have here since we have a string? So we have tension. And tension force is always from the object along the string. So this will be the tension that the string is experiencing. Great. Now, being on the presence of an electrostatic field, electrostatic force, what else do we have here? What else do we have here? Since we said that as a result of the presence of an electrostatic force, we will have an electrostatic force presence here. In which direction is the electrostatic force? In order to have a force net equal to 0, do you think that the electrostatic force will go, let's say, toward east, or will go toward west? In which direction do you think that will be? So will be, let's say, west or to the left. Okay, so this will be the electrostatic force that the charge of our interest will experience. Good. So now we have all the forces. We don't have any other forces that the charge is experiencing. This is a 2D situation, which means that, as I said, the easiest and the best, or the way that gives you always the correct answer, because it has a structure on it, is completing the table of components. So this will be force of gravity, and then tension, and then electrostatic force. Since we are done with all the forces, then we have force net. However, since the object is in equilibrium, we said that force net is equal to 0. And the 0 force has 0 components. So 0 and 0 for the horizontal and vertical. And now, based on our information, knowing that the angle here is 12 degrees and a mass is 2.30 grams, we can figure out what is the horizontal and vertical component of force of gravity. First of all, what is the horizontal component of force of gravity? Since it is a force that is going toward the center of the earth, going down, so will be 0. And the magnitude of force of, or vertical component of force of gravity will be 2.30 is in grams. We will convert it into kilograms times 9.81. So I have for the vertical component as negative, because it is going towards south, 0.022563. It's good to keep them all, especially in those cases. But, you know, at the end is the calculator that is holding on to those numbers. Now, the key point on those type of questions is that we don't know what is the tension on the string, okay? So on those cases, what you will do is you will fake as knowing what is the horizontal component and what is the vertical component of the tension. What do I mean by this? So you will fake as finding the horizontal component and the vertical component, even though of the tension, even though that you don't know what is the magnitude of the tension. So you will follow the steps. As from the tip of the vector, you will draw perpendicular to include the given angle. Whatever is along the vertical will be the vertical component, so TV, and whatever is along the horizontal will be the horizontal component, so TH. Okay, now we don't know what is the magnitude of the tension. However, we can say that this vertical component, since it is the adjacent of angle 12 degrees, is T times cosine angle 12 degrees. Agree? And then, since the horizontal component is the opposite of 12 degrees, then will be T times sine 12 degrees. This is what I mean by you will fake, quote unquote, as to finding the horizontal component and the vertical component of the tension. So now the horizontal component is positive, and it is positive T times sine 12 degrees. And the vertical component is positive as well, because it is going toward north, will be T times cosine 12 degrees. And now let's, if we take a look now to the electrostatic force that this charge is experiencing, then we can say that the horizontal component going toward west is negative. We don't know what is that value. So will be the negative Fe. And the vertical component of that force going toward west is equal to 0. Another reason why I like the table of components I think that especially for students when you are learning and introduced to new topics, it's good to have a structure, is that by completing the table of components, you now have two equations that are coming, one from horizontal and one from vertical. So from horizontal, you have positive t sine 12 degrees minus Fe is equal to 0. And from the vertical components, you have negative 0.022563 plus t cosine 12 degrees is equal to 0. So you have now that is known in math as a system with two equations, equation 1 coming from horizontal and equation 2 coming from vertical, and two variables. And the variables are t and Fe. Okay, so now how do we solve this? This is kind of an easy system with linear equations because you have two equations, and in one of the equations you have only one variable. So if we are using equation 2, we can find that tension is equal to 0.022563 over cosine 12 degrees, and whatever is this value, whatever the calculator gives us. Don't forget to change the mode of your calculator on the, so 2.31 times 10 to the power of negative 2 newtons. And then, so this is as a result of equation 2. And then let's substitute this value at equation 1. And then we will have 2.31 times 10 to the power of negative 2 times sine 12 degrees minus Fe is equal to 0. This is as a result of equation 1. And from here, we find what is Fe. So 4.80 times 10 to the power of negative 3 newtons. Notice here that we do not identify the direction of this force because we have drawn the free body diagram, so everyone can refer to what is the direction of the tension and what is the direction of the electrostatic force.